For prelims examination, for example, we should know about the most recent advancements which are happening. So, for example, knowing about ITER, International Thermonuclear Experimental Reactor. In general, you should understand the basic differences between fusion and fission. You should definitely know about National Ignition Facility, which I mentioned earlier, because that has been a remarkable progress.
Hello and welcome to the conversational video series brought to you by VisionIAS. You must have heard about and seen chemical reactions taking place, in which atoms take part without changing their identities. Now, if you go inside an atom, you'll find a nucleus. And nuclei of atoms also take part in reactions, which are called nuclear reactions. To help us understand about a particular type of nuclear reaction, which is nuclear fusion, today we have with us an eminent faculty member of VisionIAS, Abhishek Sir. Welcome, sir.
Thank you.
So I hope today you're going to tell us everything worth knowing about nuclear fusion. We'd like to begin this conversation with the basic question. What exactly is nuclear fusion?
First, you very rightly introduced this entire discussion that in chemical reactions, which you, by the way, everybody studies about chemical reaction in school days. In chemical reaction, you have rearrangement of atoms and electrons, but the nuclei inside atom, which by the way contains protons and neutrons, that remains unaffected. So that was a great point. Another very important point here is that all of the chemical reactions occur because of a fundamental interaction called electromagnetic interaction, which we have studied that part also. But when nuclei participate, when subatomic particles are reacting, when nuclei are participating in the reaction, we call those reactions nuclear reactions. And there are many nuclear reactions, the same way there are many chemical reactions, there are many nuclear reactions. Human beings are very much interested in two very specific type of nuclear reaction. The first is called nuclear fission and the second is called nuclear fusion. We are here to discuss nuclear fusion. In fact, before I introduce nuclear fusion, the most important reason why we are interested in these two reactions is because they allow us to produce huge amount of energy. That even with consuming a very small amount of fuel, you can produce huge amount of energy. And I'm going to now start with a very fundamental concept in physics, which was given by Einstein in 1905. Einstein is very famous for giving his theory called special theory of relativity. Now, in special theory of relativity, you come across many things. The most fundamental thing, of course, is that space and time are not independent of each other, right? But one of the consequences of special theory of relativity is that even mass and energy, which we think of two separate things, are not independent of each other. Mass and energy are very much dependent upon each other, and mass can be converted into energy and vice versa. Energy can be converted into mass. And we get this very nice relationship, which we very famously, that very famous equation, I'm very sure that everybody must have at least heard about it or seen somewhere. E is equal to mc squared, where E represents energy, m represents mass, and c is speed of light in vacuum. So, and remember, c is 3 into 10 to the power 8 meter per second, which means that even if I have very small amount of mass, I can produce huge amount of energy. And by the way, in chemical reactions, the mass of reactant and product does not change. But in nuclear reaction, the mass of reactant and product may change. But that is not a violation of either conservation of mass or conservation of energy. So a very important point, another important point where I can highlight here is that we have studied these two conservation laws. Conservation of matter, that matter cannot be created, cannot be destroyed. We can only convert one form of matter into another form. And conservation of energy, that energy cannot be created, cannot be destroyed. We can only convert its form. But now we need to combine both of these laws into one law, where it is not conservation of matter or conservation of energy, it is conservation of mass energy together. So mass energy together cannot be created, cannot be destroyed. So nuclear reactions in both fission and fusion, often we find that the mass of the product is less than the mass of the reactant. And then you ask that what happened to that mass, and that essentially converted into energy. And look at the value of C, 3 into 10 to the power 8 meter per second, which means that even with a very small amount of mass, I can produce huge amount of energy. So that is my starting point, that why we are interested in these two very specific reactions called fission and fusion, because we want to produce energy. Now coming to your question, what exactly is nuclear fusion? The nuclear fusion is a very specific type of nuclear reaction where we start with lighter nuclei. Lighter nuclei such as hydrogen or some isotopes of hydrogen such as deuterium and tritium, and we allow them to fuse together, hence the word fusion. We allow them to merge together, and in the process you get products like helium, and huge amount of energy is released, and that energy can be calculated, as I mentioned earlier, using E is equal to mc squared. So that is what nuclear fusion is, that when lighter nuclei are coming together and fusing together and producing a heavier nucleus, and as a result also producing a lot of energy.
Okay, thank you, sir. Now, chemical reactions, as I mentioned in the introduction and you also explained, they're very normal, very easy to see. But nuclear fusion reactions are not very usual. So, what are those unusual conditions in which a nuclear reaction is possible?
That's a fantastic question. Nuclear fusion reaction actually does happen in nature, if I include the word nature, universe. So nuclear fusion reaction happens in universe. All of these stars which we see, and there are so many stars. Think of Milky Way galaxy has few hundred billion stars, and then you have like about 1 to 2 trillion galaxies in the observable universe. So we have like huge number of stars. All of these stars are powered by nuclear fusion process. So as you rightly pointed out, that it does not occur under normal condition. And we can appreciate that actually with a very simple law which we studied in our, let's say, class 9th and 10th physics, that opposite charges attract but same charges repel. Remember that Coulomb's law, right? So think of, imagine the dimension of atom and imagine the dimension of nucleus. By the way, we cannot imagine it, we cannot literally imagine it, human imagination fails, but we can appreciate the statistical difference, that an atom will be of few angstrom. Angstrom is 10 to the power minus 10 meter, but a nucleus is 1 femtometer, which is 10 to the power minus 15 meter. So atom in itself is very small, but nucleus is much more smaller than atom. We cannot imagine either of that, but we can appreciate the statistical difference. So now imagine when these two nuclei are coming close to each other. Remember your basic school classes, that an atom has inside nucleus neutrons, protons. Neutrons are chargeless, proton has charge, electrons are revolving around nucleus. This is a very simple structure, not very accurate one, but for the purpose of this discussion, this structure will suffice. So imagine when these atoms are approaching each other, and the nuclei are approaching each other, and as they approach each other, there is a very powerful electromagnetic repulsion between nuclei, because both nuclei have positive charge, right? And to overcome that electromagnetic repulsion, you need huge amount of energy, pressure, and which occurs at very high temperature in the range of few million degrees Celsius. Only then the nuclei can overcome this repulsion, and they come in the vicinity of few femtometer. But an amazing thing happens. This amazing thing happens, that imagine two nuclei coming together, very powerful repulsion, but because of prevailing energy and pressure at very high temperature, somehow they have been able to overcome this repulsion, and they are in very close vicinity. Now here something amazing happens. There is another fundamental force in the nature which we call strong interaction. And one of the manifestation of strong interaction is strong nuclear force. So strong nuclear force occurs between protons and protons, between protons and between neutrons and neutrons, which means that it is not dependent upon charge. And strong nuclear force is more powerful than electromagnetic repulsion. But it is a short range force, which means that while electromagnetic repulsion theoretically can be felt at very large distances, strong nuclear force has a range of about few femtometer, in the range of 10 to the power few 10 to the power minus 15 meter, which means that it only operates when nuclei are very close to each other. So when nuclei come very close to each other, strong nuclear force starts operating, and nuclei glue together and they form a heavy nucleus, but that heavy nucleus will have less mass compared to the reactant nuclei, and that mass essentially converts into energy. So the prerequisite condition is very high temperature and pressure, where nuclei can fuse together, can overcome their repulsion, fuse together and produce a lot of energy. The same process happens, as I was saying earlier, that this process naturally happens in the core of star. So think of sun as a star, and sun is really huge, but about 25% of sun, the most inner layer, which is about 25% of sun, is called core. And in the core, the temperature is about 15 to 20 million degrees Celsius. By the way, even this temperature is not enough for fusion to happen, but there is something called quantum tunneling, which perhaps will be a topic of discussion in a separate conversation. And that quantum tunneling allows nuclear fusion to happen at about 15 to 20 million degrees Celsius, and that powers the entire star. So you can think of the entire star being powered by a very powerful chimney at the center, which is illuminating the entire star. And because of that, as you go to the outer layers, the temperature reduces, and the outermost layer, for example, for sun is photosphere, and that temperature will be about 5500 degrees Celsius.
Okay. So my next question was going to be exactly the same, because you mentioned stars, and we'll discuss what is the exact process in which sun is being powered, like what elements are being formed and what elements are reacting to form the new elements. But before that, could you just briefly tell our viewers what are the four fundamental types of forces so that they can easily understand?
Okay, so one of the most important question which people have asked in physics is that what are the fundamental particles? Fundamental means that I cannot go any further, that everything is made from these fundamental particles. But if there are only particles and no interactive force between them, then we would not have seen what we can see around us. So clearly particles come together and they form some sort of assembly. But in what ways they can form those assemblies, right? So we come across four such fundamental interactions. The first, which is very simple, is gravitational force, which we have studied since our school days, that objects with mass, they have this attractive force. The theory was given by Newton, which was further modified by Einstein. The second fundamental force we have studied is electromagnetic force, which occurs because of charge. If charge is stationary, it produces electric field. If it is moving, then it produces both electric and magnetic field. So we call that electromagnetic interaction. But then there is this third interaction, which is called strong interaction. And strong interaction occurs at the actually level of a group of fundamental particles called quarks. Again, that will be a separate discussion altogether, that protons are not fundamental. Turns out that protons and neutrons are made of a more fundamental particle called quarks. And these quarks have a very powerful interaction mediated by another particle called gluons, which is called strong interaction. And strong interaction is more powerful than electromagnetic interaction. And however, as I said earlier, that it is a short range force. It does not exist beyond few femtometer. And then there is another fundamental interaction which is very unusual, called weak interaction. And the discovery of weak interaction challenged so many of the existing theories in physics, which by the way is again going to be a very complicated topic. But to simplify, there are certain nuclear reactions which occur because of weak interaction. And the most famous one I can talk about is beta decay. Remember your radioactivity classes. We learned about alpha decay, beta decay, gamma decay. So beta decay occurs because of weak interaction, but even weak interaction is short range force, and in fact its range is even less than range of strong interaction. Its range is in 10 to the power minus 18 meter. And even though it is called weak interaction, it is actually much more powerful than gravitational force. So if I have to look in terms of strength, if I have to arrange them in terms of strength, then gravitational force is the weakest interaction. Then weak interaction is the second weakest interaction, is the stronger force than gravitational force. And electromagnetic interaction is much more stronger than weak interaction, but the strongest interaction in the nature is strong interaction, which allows nuclei to remain stable. That despite inside a nucleus you have protons, and ideally protons should repel, they are positively charged particle, but still most of the nuclei are stable, and the reason is strong interaction.
Okay, sir. Now the question we are expecting to know from you what exactly drives a sun. What elements are
Okay, so the most simplest element in the universe is hydrogen, because hydrogen is made of just one proton and one electron. There are no neutrons here. So hydrogen was the simplest and of course the most abundant element in the universe, right? So in star, hydrogen atoms fuse together, and the process happens into multiple stages, but I can like directly mention the end result, that 4 hydrogen atom fusing together and forming a heavier atom, which is now helium.
Okay, sir.
And in the process they also produce positrons, which are like antiparticles of electron. They produce neutrinos, and they produce huge amount of energy, which can be calculated using E is equal to mc squared. So long story short, it is hydrogen nuclei fusing together, producing helium, and as a result huge amount of energy is released.
Okay. It seems that the sun is actually a tremendous source of energy, but we can also artificially use nuclear fusion to produce that much energy. Is it possible? Is it practical?
It is possible, but I'm very sure that based on this, till now whatever we have discussed, it should be very clear that it's going to be very difficult thing to achieve. So it is possible, scientifically it is definitely possible. It is already happening in nature. If we can create the prerequisite conditions for fusion, then fusion is possible. And if it becomes possible, then it will be a great news for the entire humanity. I will come to that part also. There are 2 main approaches which people have adopted. The first approach is called magnetic fusion, and the second approach is called inertial fusion. And goal of both of these 2 approaches to attain nuclear fusion and produce lot of energy. And there are many experimental setups which are there in the world. Even India has taken certain steps in this direction. We will talk about that also. But fusion as a sustainable source of energy has not been possible till now. There is a very famous joke in physics that fusion is always in the next decade, which means that people always think that fusion will become possible the next decade. And people have working on attaining fusion to produce energy for electricity for last few decades now, but it has not been successful. And but nonetheless, there are many different approaches which are being adopted across the world.
Sir, a related theme, which is ITER. The experiment has been going on for like over some decades. So what is the progress we have made so far?
Okay, so before I answer that question, let me elaborate further about the 2 approaches I talked about.
Sure.
So ITER, which you mentioned, International Thermonuclear Experimental Reactor, that is a magnetic fusion device. So let me talk more about that first, and then I will come to the ITER part. In magnetic fusion device has different designs. The most popular design is called Tokamak. A tokamak is a toroid shape. Now, if you want to imagine a toroid shape, you can imagine a donut or you can imagine a kangal. Think of a bangle. So think of that shape which is called toroid. Inside this toroid, you create very powerful magnetic field, and you allow deuterium and tritium, 2 isotopes of hydrogen now, right? So deuterium is an isotope of hydrogen, tritium is an isotope of hydrogen. You allow deuterium and tritium to first heat up, and to heat up we use different mechanisms, and we allow the deuterium and tritium plasma to now be part of this tokamak. Why I am using the word plasma? Because plasma is that fourth state of matter where if you keep increasing the temperature, matter comes into ionized state where electrons come out, and if electrons have come out, whatever is left is positively charged. So at very high temperature, few thousand, few lakh degrees Celsius, matter is in fourth state, which we call plasma state. It is not solid, not liquid, not gas, it is plasma. So you have deuterium and tritium plasma inside this toroid shape, and you keep increasing the temperature to few million degrees Celsius. In fact, ideally we should go to as high as 100 million degrees Celsius. And then at such high temperature, fusion can happen. It goes without saying that at such high temperature, if plasma comes in contact with the wall of the tokamak, then it is immediately going to vaporize those things. We do not want that to happen. And that is where magnetic field comes into place. That magnetic field can contain them in the vacuum of the tokamak, right? It will not allow the charged particle to come in contact with the walls of the tokamak, so that fusion becomes possible. So now think about these two things, that we are essentially talking about creating temperature of few million degrees Celsius at very high pressure, and magnetic field powerful enough which can ensure that the plasma inside this tokamak is not coming in contact with the walls, and still fusion should happen. Like, there are so many prerequisites which needs to be fulfilled, which tells you that how difficult it is to achieve, right? So there are many tokamaks in the world. The most powerful tokamak which is under construction is located in France. It is a collaboration among many countries including India. So you have India, Russia, China, America, South Korea, Japan, entire European Union, UK, all of these nations coming together, and they are working on making the largest tokamak ever built in the world, which is located in France, and we call that International Thermonuclear Experimental Reactor. Regarding the progress, it is an under construction facility. The plan is that once it is built, and the timeline here for the completion of the construction is about 2030, early 2030s. So once it is built and once fusion starts, then it is going to become the largest facility which will aim to attain fusion based power. And the objective here is to go up to 500 megawatt of fusion based power. So let's see how that happens. So as of now, it is, I will say that it is an under construction facility, and many countries are collaborating together, including India.
That was quite well described, sir. Thank you. Now, where does India stand when it comes to nuclear fusion?
I think we forgot to discuss also about inertial fusion. Like, should I go into inertial fusion also?
Sure, sir. Please.
Okay. So inertial fusion is this another approach which some countries have adopted. America here is at the forefront. And in inertial fusion, what you do here is that in a very small spherical container, you keep again deuterium, tritium, and then you illuminate this deuterium, tritium with very powerful laser beam from every direction in a symmetric manner. So the container immediately vaporizes, but the deuterium, tritium inside it faces this immense pressure from all direction, and the temperature now increases to a few million degrees Celsius. And this leads to what we call implosion. Now think of explosion where objects are being thrown out. This is implosion where you have no other way. So there is a very powerful electromagnetic repulsion between the nuclei of deuterium and tritium. But because of this continuous laser beam from all directions symmetrically trying to illuminate deuterium, tritium, it leads to fusion, and that can also produce huge amount of energy. Now this is actually quite remarkable because in California there is a facility called National Ignition Facility, and 2 years ago National Ignition Facility announced that we have produced surplus energy using nuclear fusion. This is remarkable news. Why this is remarkable news? Remember, we have already established that fusion requires a lot of prerequisites. We have to start with a lot of energy first, so that I can attain temperature of few million degrees Celsius. And when fusion happens, then you are hoping that the energy which is getting produced is many, many times more than the energy you started with. Think of this as a business proposition that I spent 100 rupees. I'm expecting at least, let's say, 120, 150, 200 rupees. So, till now, people have been able to attain fusion, but they have not been able to, or they had not been able to produce surplus energy. So, in National Ignition Facility located in California, using inertial fusion with powerful laser beams, for the first time, they attained that surplus energy. But even then, remember, they have only figured out the science part. The next set of challenges will be to figure out the engineering part, that how to scale it up. Right now, they have done it on a very smaller scale, but how to scale it up so that, let's say, we can power a city, that is going to take many, many more years.
So can we say that this inertial way of going about it holds greater promise than the Tokamak design?
There is debate, there are debates surrounding it, that which is a better design, inertial fusion or Tokamak based fusion. Tokamak based fusion in fact is more popular design. There is this joint European torus in Europe. I'm very sure you have read about this term called China's artificial sun. So that China's artificial sun is nothing but a Tokamak device. Its full name is, if I'm not mistaken, Experimental Advanced Superconducting Tokamak, something like that. I might be not exactly remembering the exact name. So that is also a Tokamak, right? And even India started this. You asked a question earlier about what is India doing. So there is this institute called Institute of Plasma Research, which works under Department of Atomic Energy in India. And Institute of Plasma Research made its first tokamak called Aditya Tokamak. Aditya comes from sun. So we are trying to replicate what happens in sun. But the purpose of Aditya Tokamak was to produce high temperature plasma and to contain it. And we were successfully able to do that many number of times. And as of now, we are working on upgraded design called SST1 steady state superconducting tokamak. So we have also taken few steps in this direction, and the goal here is that, and we are also member of ITER, International Thermonuclear Experimental Reactor. So the goal here is that if ITR becomes successful, all the intellectual property will be shared with the member nations, and India will be ready to produce fusion based power, right? Will this be a better design, Tokamak be a better design than inertial fusion? They both have their own set of challenges. In Tokamak, you need to produce very powerful magnetic field to contain plasma at few million degrees Celsius. But here you need all of those powerful laser beams symmetrically illuminating a small amount of deuterium and tritium. So they both have their own sets of challenges, and only time will tell that which design is going to become more popular in the future, right? But as of now, I should tell you that most of the designs in the world is actually based on magnetic fusion design, the Tokamak design or other magnetic fusion designs which I mentioned earlier.
Thank you, sir, for telling us what exactly is going on in India regarding nuclear fusion. Now, a last question related to the concept of nuclear fusion. What are the benefits of nuclear fusion?
Okay, so despite so much of effort, fusion has not been possible, and we still are trying to attain fusion. Fusion has this benefit that it does not release any greenhouse gases, right? It's a nuclear energy, does not release any greenhouse gases. One of the biggest challenge we are facing in the world is global warming and climate change. So fusion will be an answer to that. People also, of course, already are using nuclear reactors, fission based power. But nuclear fission based power or nuclear reactors have their own set of challenges. It also does not release greenhouse gases, but it does produce a lot of nuclear waste. There is a fear of reactor meltdown if the chain reaction becomes uncontrolled, right? And all of these are challenges. How to dispose of the radioactive water? All of these are challenges. In fusion, those challenges are not there. In fusion, you do not produce long-lived, dangerous radioactive waste. Even if some radioactive waste is being produced, the radioactivity is not very dangerous. That is the first thing. Second thing, that fusion produces more power than fission, right? So for per kg of fuel, fusion will produce few times more power than fission. Fusion raw material is deuterium and tritium. Deuterium is easily available in every natural water source. Tritium can be made from lithium or other elements, right? So that is another benefit. And it can, if it becomes successful, it will be a reliable source of energy for hundreds and thousands of years without releasing nuclear waste or without producing greenhouse gases. And that is why fusion holds so much of promise.
So with all these benefits, we can surely look forward to creating or using nuclear fusion as a sustainable source of energy. So because most of our viewers are UPSC civil services aspirants, one question related to the importance of nuclear fusion as a topic.
Okay, so few things we should know. For prelims examination, for example, we should know about the most recent advancements which are happening. So, for example, knowing about ITER, International Thermonuclear Experimental Reactor, knowing about what India is doing, such as SST-1 or Aditya Tokamak by Institute of Plasma Research, that will be important. In general, you should understand the basic differences between fusion and fission. There can be questions based on that concept also, right? You should definitely know about National Ignition Facility, which I mentioned earlier, because that has been a remarkable progress in in producing energy from nuclear fusion. In mains examination, certain themes, but now you have to write answer, of course. So again, same thing, that what are the inherent benefits of nuclear fusion over, let's say, nuclear fission or other type of energy sources. And another question which you can expect here is that what are the challenges in attaining nuclear fusion, right, which we discussed. And of course, we should also know about some of the major advancements. So if there is a question on fusion in mains examination, you should be able to write about ITER, about National Ignition Facility, even about Institute of Plasma Research initiatives like SST-1 or Aditya Tokamak. So these are some of the themes which should be covered.
Thank you so much, sir. I think you could have gone on answering most of our queries and doubts, but due to the paucity of time, we're going to end the session here. We'll keep coming up with more such sessions to know everything about fusion or the keywords that you mentioned. Thank you for your valuable time, sir.
Thanks a lot.
Now, dear viewers, we hope you liked and enjoyed the session. We'll keep coming up with more such sessions. Till then, wish you all the very best.